Hello guys, welcome to this video where we're going to be examining the vector potential in magnetostatics. In this video we're going to be talking about the magnetic vector potential, which is pure, doesn't have any physical meaning in the real world, but is good to simplify Maxwell equations, especially when it comes to evaluating uh, the curl of the magnetic field, which is equals to the mu naught current density times current density. So in this case, we're gonna show in this video solely will prove that the magnetic field, as you can see here, equals to the curl of A, and the A is the vector potential in magnetostatics. So this video we're going to be plugging back the value of B, which is the curl of A, back to here, to this B here, sorry, and to show that how we're going to apply Ampere's law as well to show that the curl of my vector potential equals to mu naught current density. So we're going to introduce first the vector potential of the magnetic vector potential, which is going to be equal to the curl of A. I remember the divergence of the magnetic field is equal to 0. That's just keep in mind because you're going to be using divergence a lot in order to prove that, to do the proof theorem and to prove the theorem. And if we use the divergence, remember it's going to be equal to 0 at some points. So let's go down here. So don't worry about the blue things now. We're gonna do it later. Just put it here for now to not forget it later on when we prove the Ampere's law or the modified Ampere's law. So first we need to ensure that the divergence of B equals to 0 is automatically satisfied. So whenever you see that divergence of B is always equal to 0. The Ampere's law becomes, in this case, that the mu naught electron, I keep saying electron density, but it's current density, equals curl of magnetic vector potential, which I'm going to refer to it from now on as an A, equals to, now we apply the curl axiom, which is going to give you the divergence of A minus the Laplacian, which is a double divergence of A. So that doesn't look like Ampere's law at all. For if you like first time you're doing this thing, it doesn't look like Ampere's law. It looks like a bunch of divergence and curls, and it doesn't mean anything. It just means it just looks like lengthy. But we're gonna show that. Give me a second. Let me grab a pin here. Let's do it. That this term will go to 0, and you end up with minus Laplacian of A equals to mu naught current density, and which looked similar in this case to Poisson equation, which we did in the dielectric. So vector potentials are gauge dependent. So when we say gauge dependent means that there's multiple values of A that satisfies the equation, and we need the column gauge to solve this problem. So you may have different vectors that satisfy this equation, but we're looking for specific ones that satisfy this equation. And to do so, we're gonna introduce a new transformation. So we have like A transforms, a new vector that we'll be referring to in this case here, the transformed vector here instead of A. So instead of thinking A now, I'm going to think as an A prime, which is a transformed vector. And that's equals to A plus the divergence of the scalar vector, or the potential scalar vector. And this scalar will be useful in the process of cancellation to ace this term and be able to prove that the mu naught current density equals to minus the Laplacian of A, which is the magnetic potential vector, or vector potential, sorry. So we did that, and we still this will still satisfy this equation because it has to do with linear dependence and independence. So we know that this addition will not do much of thing. We'll just see it later on. I know like I'm throwing a bunch of things on you right now, but if you watch the video multiple times, you're gonna be able to understand everything later on. So we have the divergence or the curl, sorry, of A prime equals the curl of A, which is equal to B. We know that as a fact. So we know that. So A plus the divergence of scalar vector will be the same as the curl of A prime equals curl of A equals B, which is the magnetic field. So by using a transverse gauge or the column gauge, we end up with getting that the divergence of A equals to 0. So since the curl of it equals to B, then the divergence of it should be equal to 0. I hope you see that transverse property there. Given any A 0, which is going to be any A value that is divergent equal to 0, we can define this. So what's this? This is a triple integral, as you can see, which is very obvious. And in this, we're going to define the scalar potential. And the scalar potential is nothing but the 1 over 4 pi, which is pretty much a constant, and it's very useful in electromagnetics to know what's the value of 4 pi because you don't columns on all this stuff. It's 1 over 4 pi and epsilon and stuff like that. So 4 pi comes handy. So we got the triple integral of the divergence of A 0 or vector 0 with respect to source coordinates. So r prime is the source coordinate because you see you have r and r prime. R prime is the source coordinates. So it's going to be like x, y, and z. So it's going to be like given values like 0, 0, 0, 0, 1, which means like it's in the direction at one unit upward. And that's just an example. And r is the field point and coordinates. And r could be as well, like probably could be 0, 1, 1, 0, 1, 0. So it's in the y direction with 1 unit in the positive direction. And we do d3, so remember it's integrating over a volume. And your integrand, or not integrand, your argument of interest is going to be the r prime, which is the source coordinates. So doing this integral and really bizarre integral, you end up with that the Laplacian of A, the scalar potential should be equal to the negative divergence of A 0, which is the vector that satisfies the condition that is not equal to 0, which is this one here. So we got that A, which is, if you look back here, so let's assume the A prime now is A equals to A0, which is the vector that is not equal to 0, that is divergence equal to 0, plus the divergence of the scalar potential. So if you look here, if we get this, the Laplacian equals minus divergence of A0. And if we took the divergence of A, we take the so if you take the divergence of the whole equation, you end up with getting divergence of A0 plus the Laplacian of A in here, and this one is equal to this value. So if you do the math, just subtracting both equal quantities here, which should give you 0. Let me just scroll down here. So if you have the divergence of vector A0 minus the divergence of vector A0, that should give you 0 because subtracting equal quantities. I know there's operations, divergence, but it's going to be subtraction between them, so end up with getting 0. And that ends up with giving you the divergence of A equal to 0. And if you go back here, the divergence of A is indeed 0 because that's A here, 0, and the divergence of A equal to 0. Or you can think about A as the divergence of the scalar potential, and when you do that, you get like just like A0, and you know the divergence of A0 is just 0. So it's just back substitution pretty much. And you know that this could be written as either the third divergence, I know what they call it, like divergence to the power of 3 of the scalar potential, or you can just do the Laplacian of A or A0, and in this case that should give you the mu0 J, or current density. And that will be similar then to the, and don't forget the negative sign here from the identity. And last but not least, we get the in the transfer guide, the Ampere's law simplified to what? To the curl of B equals minus Laplacian of A, and the Laplacian of A, which is the scalar vector, the vector magnetic vector potential, should equal to the minus current density mu naught, and that's analogous to the Poisson equation right here. And now we're going to do some solutions for the vector potential. So it depends purely on the geometry and on what you're evaluating. So I mean, if you can write this down, that'll be very helpful when it comes to solve some equations or exercises. Mathematical exercises. For current density, you get mu naught over 4 pi, which is always a constant in this case. It's going to be jr prime divided by r minus r prime, dx prime, dy prime, dz prime. And r prime could be written as x, y, and z, and r as, x prime, y prime, z prime, and r, x, y, z. And remember that x is the, or r is the field point, and r prime is the source point, which is j pretty much. And for surface current, same thing, you just change it to k by integrating over the area in this case, which is d2a. This is going to be just x and y, or x and z, or y and z. You get any combination of two variables. And for a thin wire carrying a current I, is going to be the same thing, but in this case using a current instead of k, letter k, which is the current surface current density, using I, which is the current, linear current, and you divide it by the r, the absolute value, which is pretty much the distance between the source and the field points. So that's pretty much it for this video. In our next video, we're going to be doing an example. And this example will be how to derive or get the equation in the polar coordinates. Magnetic vector potential from a circular point, so you end up with getting the, I don't want to spoil it, but you'll be able to find the value of A in terms of the axis z in a polar coordinates. Thank you, and see you in our next videos.